this video, we will be discussing the development of atomic theory from the first modern atomic theory written by John Dalton up to the nuclear model of the atom. While early cultures around the world had some idea that matter could be broken down into smaller components, John Dalton developed the first modern atomic theory. Dalton was a naturalist in England during the early 1800s. He had made a name for himself with his work on gas behavior, something that we will touch on in a later chapter, but his atomic theory was the first to give a mechanistic reason for numerous observed scientific laws. Dalton's theory is divided into several concepts, or postulates, building up the first modern atomic theory. Dalton borrowed a concept from the ancient Greeks. The Greek word atomos means uncuttable and was used to describe the finite divisibility of matter by Greek philosophers. Dalton used this to coin the term atom, meaning the smallest unit of matter with distinct chemical properties. Dalton proposed that each element, a chemical could not be broken down into simpler chemical structures, was made of a specific type of atom. Each element had consistent atomic properties, and different elements had different properties. Lavoisier's construct of the law of conservation of mass states that during a chemical reaction, the mass of a system does not change. Dalton addresses this by saying that the atoms that make up matter, and therefore mass, cannot be created or destroyed. This means that the atoms in a chemical reaction do not change. Proust's law of definite proportions, or the law of constant composition, means that different samples of a given compound always contain the same elements in the exact same mass ratio. Dalton addresses this by postulating compounds are composed of consistent whole number ratios of atoms. Combining the previous postulates, Dalton was able to construct an atomic view of chemistry. The changes that occur in a chemical reaction are due to the rearrangement of atoms that are present in the system. As of the time of Dalton, the atomic view of reality consisted of atoms to be unique structures with consistent properties, kind of like solid marbles, with each element having its own type of marble. Up until the discoveries of J.J. Thomson, atoms were considered to be solid objects with compositions unique to each element. Thomson's work with cathode ray tubes showed that a variety of metals under very high voltage would emit a negatively charged particle. The particle was the same no matter the source metal. Therefore, Thomson considered the idea that atoms were not solid objects, but rather there were small negatively charged particles he called electrons present in all atoms. Thomson developed a new model for the atom, taking into consideration the existence of the electron. Since atoms are generally not electrically charged, Thomson made the bulk of his atoms positively charged matter, with negatively charged electrons embedded into this positively charged matter. This is called the plum pudding model, though I doubt any of you know what a plum pudding is. So I consider it more of a cinnamon raisin bread model, with the positively charged matter being the bread and the electrons are the raisins embedded in it. Thomson's student, Ernst Rutherford, developed an experiment to test Thomson's model. He shot a stream of the recently discovered alpha particles at a thin sheet of gold foil. While Thomson's model predicted that the majority of the particles would pass straight through, it did not predict the number of particles that were deflected at very large angles. The only explanation was that the alpha particle, a dense, positively charged particle, must have passed near a very massive, relative to the alpha particle, positively charged object. To address the results of the gold foil experiment, Rutherford proposed that the positive mass of the atom must be contained in a dense central nucleus, with the electrons existing in the mostly empty space surrounding the nucleus. Further experimentation showed that the nucleus contained discrete positively charged particles that were named protons. Frederick Soddy made a discovery that directly contradicted the postulates of Dalton's theory that all atoms of the same element are identical. Soddy discovered that different atoms of the same element can have different masses, a phenomenon he named isotopes. Thomson showed that these isotopes occurred in non-radioactive elements also. The last subatomic particle, the neutron, was discovered by James Chadwick as an answer to the problem of missing mass in atoms. Since the mass of the electron and the proton were known, it was possible to determine the predicted mass of atoms. However, the predicted mass of atoms were half or less the actual measured mass. Chadwick proposed a new subatomic particle to account for this mass. Since the particle could not be manipulated by electrical fields, it had to be electrically neutral and was therefore named the neutron. Considering all the previous work, our atomic model has matured into the nuclear model of the atom. The central nucleus of the atom is composed of the positively charged protons and the electrically neutral neutrons. The majority of the space occupied by the atom is empty space, and in that empty space we find the small negatively charged electrons. The number of protons determine the type of element the atom is. The neutrons help maintain the stability of the nucleus by gluing together the positively charged protons, and the chemical bonding of the atom is determined by the number and arrangements of the electrons.